Hello, everyone. I'm quite excited to do this lecture because we're moving on from idealized black holes, where we only consider mass and charge. And in this lecture, we will talk about more astrophysical black holes, where we include an extra parameter, namely spin. And we will derive the Kerr-Newman metric, and we will talk about the geometric and physical properties of spinning black holes. So let's go. The outline of this lecture is as follows. As always, I will summarize what we did in the last lecture. Then I will talk about how we derive the Kerr-Newman metric using standard methods like differential forms, and how to use computer algebra systems to compute the Ricci tensors. But I will show you why this is relatively difficult, and we don't do this nowadays because it's quite tricky to do, and even for computers, it will take quite a long time. So I will show you another formalism, namely the tetrad formalism, and another method of obtaining the Kerr-Newman metric, namely using the Newman-Janis algorithm. And subsequently, I will discuss some important surfaces for Kerr-Newman black holes, namely the Cauchy surfaces and the ergosphere. And the ergosphere is quite special because we can extract energy from spinning black holes from a process called the Penrose process. And finally, I will talk about the singularities for Kerr-Newman black holes, and I will show you a sketch of a proof for black hole uniqueness theorems for a more restrictive case. So recall in the last lecture, we discussed extremal Reissner-Nordstrom black holes, and this is for black holes with mass equivalent to the magnitude of the charge. So the metric is as follows. And we found, unlike the Schwarzschild case, the extremal Reissner-Nordstrom black hole cannot yield wormhole solutions, and this is because the proper length for constant t, theta, and phi diverges, and this corresponds to a wormhole with an infinite throat. And to understand the topology near the horizon, what we can do is we can set r is equal to m, which is the event horizon, and add some small parameter, lambda m. And what we can do is we can expand to leading order, and what we obtain is the following metric. And this is called the Robinson-Bertotti metric. And this part corresponds to the anti-de Sitter region, and this part corresponds to a spherical region, as it's the metric of a two-sphere with radius m. And we see that this has topology ADS2 cross S2. And I can show you what this kind of looks like on an embedding diagram. So in last lecture, I showed you this embedding diagram obtained from Rial's lecture notes. And these two regions correspond to the spherical part. And later, I will probably prove using Hawking actually proved that for any black hole in 4 dimensions, the event horizon must have a topology of S2. And it only works in 4 dimensions because it utilizes something called the Gauss-Bonnet formula, which only works in a certain number of dimensions. But I can also show you the ADS2 region, and this looks like a cylinder on an embedding diagram. And I obtained this figure from supergravity book that I discussed in the last lecture. And with this, I also discussed how the extremal Reissner-Nordstrom black hole is the simplest case of supersymmetric brane solutions, and how they are supergravity solutions. So, but before I discuss that, I talked about the geometry of the global geometry of extremal Reissner-Nordstrom black holes. And we can see the global structure using Penrose-Carter diagrams. And to do this, we convert to advanced or retarded null coordinates, and then we further convert to Kruskal-Szekeres coordinates. And by doing this, we maximally extend the geometry, and we can obtain an infinite Penrose-Carter diagram. And the only ones that we should take seriously are the ones not obtained by analytic continuation or isometries. And this is because the other ones are they do not, well, basically they violate strong cosmic censorship. And I discussed this 2 lectures ago. We also I just mentioned how extremal Reissner-Nordstrom black holes are examples of supergravity theories. And we can see this by making the Reissner-Nordstrom metric spatially conformally flat. And we do this by making basically writing it as follows. And in the last lecture, basically, in many lectures ago, I showed that the Yamabe equation tells us that spatial conformal flatness implies that the nonlinear Einstein equations can be converted to a linear Laplace equation. And this is akin to the concept in electromagnetism, where if the electric potential satisfies the Laplace equation, we can superpose point charges. And in this case, what we can do is superpose masses, and we obtain something called the Majumdar-Papapetra solution, where Mi, so basically you can sum over different masses to obtain multi-black hole solutions. So what this looks like on a Penrose Carter diagram, basically you can conjoin two black holes together, and what it does is it conjoins the Penrose Carter diagrams, and you can see the causal and acausal regions. And what you can do is you can also draw a space-time diagram. And what happens is this looks like a set of light cones. So this looks like a light cone, and this is a light cone. And it tells you it basically conjoins the light cones together, and it tells you the causal and acausal regions. So afterwards, I discussed supergravity, and I proved that space-time curvature obstructs global supersymmetries. And the only way that we can preserve supersymmetry with space-time curvature is to construct local ones. And in order to do so, the idea is similar to that of using frame fields or differential forms. And that is we choose a set of coordinates that is locally flat. So if I so this is a curved manifold. And what happens is I pick a set of coordinates on this manifold such that it looks flat in a certain region. So in this region, we can preserve supersymmetry. And by doing so, we can obtain some interesting properties. So I also discussed how the relationship between killing spinors and BPS states. So a killing spinor psi is basically a spinor is a killing spinor if the spinor-Lie derivative vanishes. And I showed that this is equivalent to a BPS state. If you don't remember how to do that, you can look at the last lecture. But I showed that the Majumdar-Papapetra solution has basically the relationship between that and superconformal algebras is that it has four real components, namely P alpha, M alpha beta, Q alpha, and S alpha. So the first one corresponds to linear momentum, the second one corresponds to angular momentum, and the last two are conserved supercharges. And what happens is we find that the Majumdar-Papapetra solution preserves 4 of the 8 supercharges of the n equals 2 superalgebra, and thus it is called a half BPS state. So in this lecture, I will derive the Kerr-Newman metric, and I will illustrate 2 methods to derive it, namely the methods of differential forms and using computer algebra systems. The first of which is extremely tedious, as the metric has non-diagonal terms associated with frame dragging, and the non-diagonal terms, well, basically it is harder to write the orthonormal bases and guessing the spin connections because essentially, actually, you cannot even guess the spin connections. You need to solve a set of simultaneous equations, which is not easy to do. And as always, I will show you how to do some of these, but I will leave the rest as an exercise to the reader and list them out later. The first step is to write an axisymmetric metric about phi, and this is written as follows. Basically, we have the diagonal terms, but we can have a term, a cross term, basically with dt d phi, and we can also factorize this as follows. So we obtain, we can write the metric like this, and then I squared these because when we obtain the orthonormal bases, we need to take the square root. So it's easier to actually square them and then take the square root later. So now from the lecture on Birkhoff's theorem, we know how to write the orthonormal bases as orthonormal bases. And to make this easier, let me write this as one dmu. So this as one form. And then we obtain the following orthonormal bases. So basically, this is done by square rooting each. This should be dt squared, by the way. This is a mistake. So dt squared. So if we square root this and square root this and square root this, we obtain these. And using Cartan's first equation, we obtain the following. Using this is Cartan's first equation. So by using Cartan's first equation, we take the exterior derivative of the orthonormal bases, and then we try to, well, in Birkhoff's theorem, in the lecture on Birkhoff's theorem, we could guess what the spin connections are, but it is not easy for the Kerr-Newman metric, and I will illustrate why this is the case later. So let us do the trickiest component, namely this one. So I took the exterior derivative of this component, and you obtain this really ugly expression. And what you can do is, using these definitions, you can rewrite them in terms. So basically, you replace d theta with 1 over e theta. So you can replace these with the following. And then what happens is, to determine the spin connections, we first need to write the connection 2 form, namely this one. This should be lower index, by the way. So then we solve the simultaneous equations for the spin connections, and we obtain 6 non-zero spin connections. And from here, the Riemann tensor in orthonormal bases. To determine this, we need to use Cartan's second formula. And this is not easy to do because there are 20 Riemann tensor components. And doing this by hand will take many, many hours. So I will not do it in this lecture. Therefore, I will say the derivation is left for the viewer. And to see the full derivation in gory detail, I refer you to Chandrasekhar's mathematical theory of black holes. And if you would like to see any derivation, for example, for Schwarzschild black holes, Rice-Nordstrom black holes, the Tolman-Oppenheimer-Volkoff solution, anything that is tedious with black holes, you can refer to this book. But before I show you the more efficient algorithm, I will show you another way to compute the Riemann tensors and the Ricci tensors in Mathematica. So it is important to know how to do this, because in research, it is quite rare that we will be able to do these complex calculations by hand. And additionally, if you wanted to change the metric, it is easier to streamline in this way. So let me swap screens. So this is the Mathematica notebook, and I did modify it, but actually I would say I have to give credit to my friend at HKU, who's also a graduate student. And he told me that he doesn't want me to mention his name, but I can use his script, so I won't mention his name. So basically, what you have to do is, first, you have to clear the definitions of the variables you're using. So I'm using time, radial coordinates, angular coordinates, and then the spin, mass, and charge. So I need to clear these just in case I use them in another Mathematica script or somewhere here, then I need to clear these definitions. Then I need to define some helper functions, and one can determine, so one helper function is to determine the length of the array, and the other one is to compute the inverse. So basically, to do this, you just type the command length and then you put the coordinates in. And then the next one is just to compute the metric inverse. So the metric here is basically, we define the metric as an array later. So this is a multi-dimensional array. And then what we can do is we can take the inverse by using the inverse function. And then the simplify is just to make the expression look a little nicer. So afterwards, we have to define the coordinates in the metric. So the coordinates are t, r, theta, and phi. And then the metric, okay, so in this case, I want to illustrate that we're trying to derive the Kerr-Newman metric. So we don't actually know what these are, but there are diagonal terms. So I labeled them by arbitrary functions, but we also know that the non-diagonal terms, basically the frame dragging terms of dt d phi, must be symmetric. So dt d phi must be this one, and then d phi dt must be this one. So we can press Shift Enter to print the metric. And from here, we need to write an algorithm that computes the Christoffel symbols. And how this works is we first use the definition of the Christoffel symbols to compute the partial derivatives. And afterwards, we loop over all coordinates to obtain all the Christoffel symbols. And the reason why I opted to use Lagrangians and differential forms in the previous case is because we were doing it by hand. In this case, you can definitely use the definition. But I would say if you did this by hand, it would be very, very difficult. So I will show you the code. So basically, to define a function like this, I use module, and then I put dimensions here, and then the metric here. So basically, then we need to, so basically the simplify function simplifies the overall expression. So then we take half times so this is the definition. The inside here is the definition of the Christoffel symbol, and we take half times the metric inverse, and then we take multiple partial derivatives, and then we loop over all these different coordinates, and then I will print the result for you, and I will exclaim that it will look ugly. So here it is quite long. You see these are multiple Christoffel symbol components. So here, but this is not even the worst part, because then you have to compute the Riemann tensor, and the Riemann tensor contains partial derivatives of the Christoffel symbol and quadratic terms of the Christoffel symbol. So we do the same trick, right? We loop over all coordinates, but we use the definition of the Riemann tensor in this case. So this is it. So if you want to look at this code slowly, you can take a look. And then what happens is, if I press Shift Enter, you will see that the expression is very, very long. And I'm not sure whether this will crash my computer, but let's see, show all. Okay, so it didn't crash my computer, but you can see the expression is extremely long. So this is the Riemann tensor, and the Riemann tensor has, so it is a 4 to the power of 4, so 16 squared is 256, so there are 256 components here. So then what we need to do is not really 256, but some of them, because the Riemann tensor is antisymmetric. So yeah, I don't remember how many exact solutions, but if you just naively take 4 to the power 4, you get 256 components. But the Ricci tensor, on the other hand, is, so what you need to do is you need to contract the second and fourth indices. And what you do is here, you sum over the second, fourth indices, and then you put it in from the definition of the Riemann tensor. And then you do the same trick for the Ricci scalar. Is basically you contract it with the metric, and then you can obtain the Ricci tensor and the Ricci scalar. So I sincerely hope that this does not crash my computer. Okay, so we obtain another complicated expression. So if we show all, you can see it's also very long. So the Ricci tensor is, so this is a 4 by 4. So there should be 16 components, but 16, then a lot of them. So there should be 16. Yeah, so a lot of them are degenerates. So basically they're the same. So I have actually instead of no, that should be fine. So this is the expression for the Ricci tensor, and you can see that it's quite ugly. Actually, yeah, there should only be 10 independent, 10 independent components, because the metric is symmetric. So 16 minus 3 plus 2 plus 1, it should be 10 components, yeah. So there should be 10 Ricci tensor components, and this is the expression. So it looks extremely ugly. And sure, essentially what you want to do is you want to set each component to 0 and solve a set of coupled nonlinear partial differential equations. And people have done this by hand in the past, so it's possible to do, but it's extremely tedious. And even for Mathematica, I assume that doing this kind of calculation will be difficult, because you have to solve a set of matrix equations for nonlinear PDEs. So let's go back to the slides. So generally, deriving the Kerr-Newman metric is a pain because of the non-diagonal frame-dragging terms. However, to reduce the complexity of this calculation, what we can do is we can use the Newman-Janis algorithm. And the first step is to write a spherically symmetric seed metric, so in advanced null coordinates. So essentially Eddington-Finkelstein coordinates, and this is the following. And the seed metric that we will be using is the Rice-Nordstrom metric. So this one, where f of r is this, and g of r is 1. And the next step is to use the method of null tetrads. So basically, I write g mu nu as a set of, so basically the null tetrads are a set of orthonormal bases, and the g mu nu can be written as follows, and they must satisfy the following conditions. Basically, L alpha times N alpha, or N alpha times L alpha must be -1, and the multiplication of M alpha and its complex conjugate must be 1. So additionally, they must satisfy all the other components must vanish, and for not all, but like these components must vanish. And for Ricci-Nordstrom, we can write the null tetrads as follows. So L mu is equal to partial mu, this as n mu as this, m mu is this, and then this is just simply its complex conjugate. So notice that m mu and m bar mu are very similar to the generators of spherical harmonics. And interestingly, this gives rise to gravitational radiation. And this is why we call binary black holes the hydrogen atom of astrophysics, because you can write the gravitational wave signatures for the ring down modes as spin-weighted spherical harmonics. So the next step is to make a set of complex coordinate transformations, and we do the following by basically we set r to r plus ia cosine theta and u to u plus ia cosine theta, and the other quantities are invariant. So the motivation behind this is we want to have a limit where a equals 0 recovers the Ricci-Nordstrom solution, and moreover, there must be some dependence on theta because the system is axisymmetric. So thus, if we obtain, so the reason why we make it depend on theta, because if the system is axisymmetric, it should not depend on phi. So thus, we have the new set of null tetrads. So L mu is this, N mu is this, and then M mu is this, and where we have rho squared is equal to R squared plus A squared cos squared theta. So I will compute 2 of the metric components, and the rest will be left as an exercise to the viewer, as the principle is essentially the same. So the G mu mu component is given by the following, and M mu and M bar mu cancels because they are the sum of symmetric and anti-symmetric parts. And the last 2 terms vanish, and we will see that L u and u is equal to this, and therefore G u is equal to this. So for the u r component, we can see that L u has no r components, so the second term vanishes. Additionally, mu and m bar mu is similar to the previous case, so it has u and r components. However, since they have opposite signs with equal magnitude and taking the anti-commutator of the complex conjugate, they cancel each other, and as a result, this is equal to 1. And since the metric is symmetric, we only need to determine 10 independent components, and the others can be deduced by symmetry. So from this, we find that the Kerr-Newman metric in advanced null coordinates is as follows, where delta is equal to this quantity. And recall, the point of relativity is that the laws of physics are observer relative. So in advanced null coordinates, this corresponds to an observer who is going into the black hole. However, astrophysically, we cannot probe something that has passed the event horizon. Therefore, to understand the physics of Kerr-Newman black holes, one needs to write the coordinates that corresponds to an observer outside far from the black hole, and making the coordinate transformation dt is equal to du plus this, and then d phi is equal to d phi plus a over a delta of dr. Then the Kerr-Newman metric in Boyer-Lindquist coordinates can be written as follows. So we can see that there is a cross term dt d phi, and this corresponds to the frame dragging term. And this has been observed observationally by gravity probe B. So the conventional wisdom is that nothing can escape once it has passed the event horizon. But miraculously, however, there is a region for spinning black holes where energy can be extracted. And this region is known as the ergosphere. And the process by which the energy is extracted is known as the Penrose process. The ergosphere compels any matter inside it as an observer from outside to move in a direction parallel to the black hole spin. Another way to look at this is using Hawking's area theorem. So the area of a Kerr-Newman black hole is given by the following expression. And Hawking's area theorem states that the area of a black hole cannot classically decrease, meaning if the mass of the black hole were to decrease, the area, and for the area to remain constant, the angular momentum must increase. So this increases the rotational kinetic energy of the black hole. So mathematically, the ergosphere can be defined as the region where GTT changes sign, as the time translations encodes information about the energy. To determine the radii for the ergosphere, we simply set GTT to 0, and we obtain a quadratic equation as follows, with the solution given by this. And this corresponds to the inner and outer ergosphere. So the positive solution corresponds to the outer ergosphere, and the negative solution corresponds to the inner ergosphere. So similarly, we can solve for the event horizons by finding the regions where GRR diverges. So we can set delta to 0, and we yield that the inner and outer Cauchy surfaces are as follows. And given that the cosine function is bounded by 1, we find the following inequality. So basically, the inner ergosphere is smaller than the inner Cauchy surface, and then the outer Cauchy surface is greater than the inner Cauchy surface, and the largest one is the outer ergosphere. So I generated this animation in Mathematica some time ago, and I will show you what it looks like. So basically, this is a cross-section of a black hole with varying spin. So as the spin increases, we can see that the black hole is deformed. See, and then what happens is the black hole, so the inner ergosphere increases, the Cauchy horizon increases, and the event horizon increases, but the ergo surface decreases. And the reason for this is that we want to preserve the total area of the black hole from Hawking's area theorem. So by changing the spin, we also change the shape of the black hole, and we change the spherical geometry to more of an oblate spheroid. So now I will talk about black holes' singularities. So basically, the Cauchy surface corresponds to coordinate singularities in Boyer-Lindquist coordinates. However, recall from the very first, the very first lecture, it can be removed by a set of coordinate transformations. And to concretely classify singularities, we need to compute invariant scalars, as vectors and tensors are coordinate dependent, but scalars are invariant under coordinate transformations. Therefore, we compute the Kretschmann scalar for the Kerr-Newman metric. So the Kretschmann scalar, I will not show how to derive this. This is extremely complicated. You can compute this yourself using Mathematica, but you can take this by faith from me, or you shouldn't actually. You should actually just compute it yourself. But I will tell you that it is as follows. So where the Kretschmann scalar is basically the contraction of the Riemann tensors, and observe that the Riemann tensor is singular when basically this denominator goes to 0, and hence the coordinate singularity is at r equals 0 and a equals pi over 2. This is called a ring singularity, or a ringularity for short, as the curvature diverges in the equatorial plane. And to see this more clearly, one can convert to something called Kerr-Shield coordinates, or oblate spheroidal coordinates. Doing the latter, we can convert r to r plus a, and theta is invariant, which means k diverges at r equals a and theta equals pi over 2. And this means that the size of the ring singularity is solely dependent on the spin of the black hole and not on its mass or charge. So from a couple lectures back, we showed that the extremal Ricer-Nordstrom black hole, basically extremal black holes in general, for r equals a, not r equals a, sorry, m equals a. This is a mistake. M equals a, one can have the surface gravity equal to 0. And this implies that a naked singularity can be generated in a finite number of steps. And thus, to obey weak cosmic censorship conjecture, the radius of the ring singularity must be bounded by between 0 and 1. So what does this look like in oblate spheroidal coordinates? So basically, this describes the geometry of the black hole. And we can see that this little ring here describes a singularity. So this is a geometric depiction of what a singularity on a spinning black hole looks like, because we have so basically this is axisymmetric. So this is symmetric about the z-axis. So in previous case, we would like to write it in spherical coordinates. But since we have a spinning black hole, what happens is the black hole actually starts to compress, kind of like it looks kind of like an apple. So basically, then what happens is we obtain a ring singularity in the center. So this is an interesting property of spinning black holes. So now let us end the lecture with a discussion of black hole uniqueness theorems. So like the Schwarzschild and Ricer-Nordstrom solutions, the Kerr-Newman metric is actually a unique solution to the Einstein-Maxwell equations for a stationary axisymmetric spacetime. As mentioned in previous lectures, if you want to see the full detail, read Mark Heusler's book on black hole uniqueness theorems. And although uniqueness is quite tedious to prove, I will show you the style of proof by proving a restricted problem that can be generalized. And the idea is to consider a static solution to the Einstein equations coupled to scalar fields. And one will find that by imposing asymptotic flatness, a single black hole solution will have no scalar fields. So one might naively think that given a black hole solution can act as a source of magnetic fields, electromagnetic fields, they can also act as source of scalar fields. However, this turns out to be false. To generalize this, we can generalize this by trying to prove that black holes can act as sources of other fields, and one will ultimately find that this cannot be true. And basically, they can only be sources of gravitational and electromagnetic fields. So let us consider a static asymptotically flat metric. And for this, the killing vector is as follows. And hence, we can choose a set of coordinates given by the following metric, where v is a function and hij is the first fundamental form. And given that psi, so this clearly corresponds to time translation. So psi I is time-like, so the killing vector is time-like, and hence, v is greater than 0 away from the horizon h, and by imposing asymptotic flatness, as r approaches infinity, hij is equal to v and it is equal to 1. So since light cones are tipped over at the horizon, however, we know, well, sorry, this is a grammatical mistake. So since the light cones are tipped over the horizon, we know that the horizon is and given that we know that the horizon is a null hypersurface, therefore, we know that v equals 0 on the horizon. So for classical field theories, the equation of motion for scalar fields obey the Klein-Gordon equation, which is given by the following. So this is the D'Lambertian or the wave operator, n minus m squared. So this is a this is still a homogeneous differential equation, but it has this extra term. So by writing the action, one can derive the energy momentum tensor, and it is written as follows, and hence the Einstein equations coupled to scalar fields is given by the following expression. So given that the metric is asymptotically flat, the energy momentum tensor approaches 0 as r approaches infinity, and hence the scalar field must be asymptotically proportional to this and must die off even faster. So now the trick is to come up with a suitable integral identity, and a simple one is as follows. So basically, we multiply phi, or the scalar field, by the Klein-Gordon equation, and then take the integral over the manifold, over the volume of the manifold. So by integrating this over the region where t equals constant, namely m, this yields the integral I is equal to 0. And now by performing integration by parts, we obtain these two expressions for the integrals, where sigma is the boundary of the surface of partial m. And for convenience, we choose we integrate over the sphere. So this is the integral over a sphere. And since there is no contribution from the boundary term at r to infinity, since this, so basically given this, there's no contribution from the boundary term at r to infinity, because this clearly, this factor dies off at infinity. So there is another boundary term at partial m, and this vanishes because of this inequality, and this inequality is obtained by Cauchy-Schwarz. And given that ni is a null vector on partial m, then ni contracted on itself is equal to 0. And since this is 0, this must be bounded by 0, so this is also 0. And hence a partial m. So basically, this is equal to 0, right? But this squared quantity cannot be negative. So the smallest value it can obtain is 0. So this must be 0. And on partial m, and therefore the integral reduces to the following. There should be an x here, so this is another mistake, sorry. There should be an x here. And since hij is positive definite, and hence this tells us I is negative definite, and equality holds if and only if the scalar field vanishes. However, there is an exception. Basically, I is equal to 0 for m equals 0 and phi equals constant. And in any case, though, both solutions correspond to the vacuum solution, T alpha beta is equal to 0. And this proof is remarkable, as it implies that for spacetimes to be static and asymptotically flat, one requires that there are no scalar fields. Physically, this means that the metric can be only dependent on the intrinsic physical parameters of the black hole. But once again, this is not a complete proof, but it is a sketch of the style of the proof. The full proof is far trickier, as you have to consider far more than scalar fields that satisfy quadratic potentials, and you have to consider more intricate inequalities. But the whole point of this exercise is to show you the technique of how this proof is constructed. And if you really want to prove this rigorously, I suggest you read Heusler's book on black hole uniqueness theorems. So that concludes this lecture, and in the next lecture, I will talk about more of the novel features of Kerr-Newman black holes, and I will show you the global geometry of Kerr-Newman black holes by writing the metric in either null coordinates and then converting it into Kruskal-Sekaras coordinates. So I hope you learned something, and see you in the next lecture.